All right, so before we start this problem, we have to look up some data. And we get the heat of sublimation, or the internal energy change of sublimation, is equal to 180 kilojoules per mole. We need to get the CN lost. And we saw from our prior examination that we're going to lose 4 on our coordination number, and our bulk coordination number for, and actually something has to be given here. And we have to look up what crystal structure this is, and we find out that the crystal structure for calcium is going to be FCC. So the bulk coordination number is going to be 12. So the only thing we need now is to figure out what this is. And the two things we need to do are to look up what the unit cell is and do an analysis of what that face of that unit cell looks like. So let's do that now. So first, we see that this distance is 560 picometers. And unit cell sizes are easy to look up because they're easy to determine using X-ray crystal diffraction. So they're very well known for most materials. So we said this was FCC, so let's go ahead and draw it. We have an atom on the face here. We have corner atoms. Okay, you get the idea. Okay. So if we look at this, we'll call this this is the 100 face. But how many atoms are in it? Because A naught, let's call this L. A naught is equal to L squared, the area of the face, divided by the number of atoms in that face. And if we look at this, we say, okay, there's 5 atoms, but remember, some of these are fractional atoms. So the number is going to be, this atom is completely in the face, so that's going to be 1. Each of these is only a quarter of a circle, so it's only a quarter in there. So 1/4 times 4 is equal to 2. So there's 2 atoms in the face. So with that, we can now figure out what is the size of one of these faces. So A naught is going to be 560 picometers squared. So 560 times 10 to the negative 12 meters squared. And then we divide that by 2. And so A naught is going to be 1.57 times 10 to the negative 19th meters squared. And the reason we need to have A naught in terms of just one single atom, the area per atom at the surface, is that this we divided by Avogadro's number. This was energy per mole. We're now converting it to energy per atom. So we're going to take the energy per atom, divide it by the area per atom to get energy per area, or surface energy. So that's why we needed to do this little calculation here. Okay, so we have all the pieces we need. Let's put them together. So we said we lost 4 out of 12 interactions. We had an energy of 180,000 joules per mole. We have an area of the per atom of 157 times 10 to the negative 19th meters squared. and Avogadro's number is 6.02 times 10 to the 23rd per mole. All right, so we can see that our per moles are going to cancel, and we're left with joules per meter squared, which of course is going to give us a surface energy. So we get 6.3 10 to the negative 1 joules per meter squared, or typically we put this in millijoules. So 630 millijoules per meter squared. And so notice that this is much higher than we see for things that are not held together by metallic bonding. And it's even higher than mercury, only about 2/3 of this. Of course, mercury is weaker bonded as it is a liquid. Calcium is a relatively soft metal. If we go to harder metals, we'll see that we can get surface energies of more than 1,000 millijoules per meter squared.